I'm based in Warsaw, and today I'm going to tell a little bit how you should write your queries in BigQuery so that can run faster and then so that they cost less. You may know or not know, like basically in BigQuery we charge for how much computational power you consume, so it's better for both for us and for you, so that you compute as little as possible, and that's it's all about. The plan for today is that I will give a little bit of intro how BigQuery is working, what is behind, what is the architecture, but it's just 2 slides of some theoretical background. How the query is executed, what are the steps that we are taking to deliver the query results to you, and then I will go to some 15, hopefully handful tips, what you can do to your SQL query so that to accelerate them and to save some money. I will be switching later on between the slides and some coding, so you could see how the query responds, what can we do with SQL to make them better. Right. Generally, 2 things that you need to know about BigQuery. One, basically, BigQuery you probably all know. This is the data warehouse provided by Google, built by Google. Back 20 years ago, something, it was mainly built for our internal purposes, but then we published it live, and this is available in Google Cloud today. And what is unique with BigQuery is that it is all about the distributed computing. Yes, so we separated all of the storage when we store your data, all of the hard disks, millions, I don't know, zillions of servers that are specific to storing the data. This is separated from the compute. Yes, so we have different machines that do the computations, different machines that store the data. We can scale them independently. You can also scale them independently. So if you have a lot of data, you can have, but you don't process them too much. You can have a lot of. You pay for storage, but you don't pay for compute. On the other hand, you can have not that much data, but you can heavily process them, and then you don't have to pay much for storage, but you pay for compute. To make it work, like usually when you have such a old-fashioned database under your desk, you could have all of that in one computer. You could have a hard drive and a computer and a CPU and some cable between. Here in BigQuery, between these storage servers and the compute servers, there's a petabit network that it's all like mimic somehow one computer. There's a cloud as a computer. And the other thing you need to know about BigQuery is that we store data in a columnar storage. So in opposition to traditional Postgres or MySQL, every column of your table is stored in a different set of files. What it means, it doesn't look like, because usually the traditional databases, you could think about it like a CSV file, you load the record, you have all of these 30 columns. It's not the case in BigQuery or in any other columnar storage data warehouses. Every column is stored in a different file, so that it's important to remember that you don't have to load all of your columns. If you don't need them, don't touch them, yes, basically, because loading or reading all of these columns will cost you additional CPU, additional money. Having said that, we can take a look how these queries are run by BigQuery. So let's imagine we have a quite simple query when we are looking for the table that holds all of the New York bike rentals in New York, city bike trips. We want to take all of these trips that started somewhere around Broadway, and we want to count all of them. And how this is done in BigQuery, all of this data are stored in our file system, and then the whole distribution part comes in, yes? So we have a lot of, we call them slots, so some machines. Here are the four of them, but usually there are hundreds of them. Each of these slots reads part of your data, yes, because probably there are some millions of city bike trips started in Broadway. Every slot just reads part of this data from the disk. It is trying to compute, like count all of how many of rows there are in this part, and all of these slots do their job. Then there is the part of the shuffle when we need to combine all of this data read from different slots, and then the final slot will just add all of these numbers that were computed by this in the previous stage. Yes, so this is like two stage. So one slot could say I found 10 writes, I found 0 writes, I found 3. Altogether, it was some number that we can compute, and it is written to the file system. Every query that we are running in the BigQuery just stores the results of the query in some temporary table or a permanent table if you wish. So knowing that, we can go to these tips, how you can work on your queries, how you can improve them if you want to accelerate or save your money on this processing. For all of these examples, for all of these queries, I have a very simple data model. So suppose that we have a table with products, the ID, SKU, product name, category, price, brand status, very, very common columns. And we have some transactions that were made. So we can think about some internet store and any kind of e-commerce solution. And for the transaction, we have product ID, that is a foreign key for the product. And we have some information about price, amount, date of the transaction, some additional text, comment, and so on. For the sake of this exercise, I prepared a table that has around 300,000 products and around 500 million transactions. So this is the scale of BigQuery that the query should take a couple of seconds so that we can see that, but it's that we don't have to wait too long. So going to the first example, I will try to go through the SQL queries as you write it. Yes? So if you start with select, the first recommendation is never run select star. Like usually, you don't need all of the columns. Just because it's the easiest way to write a query, select star from the table, it doesn't mean that this is the best way. If you really don't need all of the columns, it's not necessary. Even, of course, it's best. You can just write all of the columns comma separated, but you can also have this notion of except. Yes. So now we can switch to see how this looks like. This is a BigQuery. I tried to zoom in the screen so that you can see that. So suppose that I want to take all of the transactions that were done in this year with some status refunded, and then I run the query, and I will have some results. Yes, so I have some results. This is around 3 million transactions, 3 million records returned. And here, BigQuery shows me that generally the query took 6 seconds, but it consumed around almost 4 minutes of the slot time. Yes. So if you even divide this for 240 seconds by 6, you can say that it was around 60 machines that were working on your query. And for this case, it's maybe even more important to take a look at this job information, and you can see that this query processed almost 83 gigabytes of data. And if you run your queries with on-demand model, so the very first default model of BigQuery, you are built by this number, by terabytes processed, or terabytes built, in fact. So you want to minimize this number. So if you think about it, and you really don't need to have all of your columns, let's say there is some free text comment that people were leaving, and you run this query again just without this column, then probably the query will not take much shorter. It's 5 seconds versus 6. It's a little bit less slot time consumed, but you can see that instead of 83 gigabytes, it's only 34. So it's like the cost is less than a half. So this is very easy patch to apply. We can move forward. We're writing the query. It was select. Then you go for the from. You have to provide the tables, and very often this comes with joins. And you have to know that there are at least 2 types of joins that we do when you are providing two tables that you want to take data from. So if you have 2 large tables that you are trying to join, it's relatively heavy operation for BigQuery to join the tables. So suppose that you have, like here, you want to join transactions and products, and if the products table was a really big one, then every slot is, again, reading just part of the data. So this green slot can read some transactions, this other slot, other part of the transactions, but then this green slot will just read part of the products and the other part of the products. And then there is a heavy job, like noted by this cloud, to the shuffle, how these nodes must exchange the data so every transaction meets their record, yes? So there's a lot of things of how these tables need to, how these slots need to exchange data so that the join matches. So this is the shuffle join. This is not the best scenario. We would like to minimize the number of rows that are being joined. The better scenario is when you can run the small join or the broadcast join. So suppose that you are joining a big table with transactions with some smaller table. Let's say product category is smaller. Probably products also are not that big. So basically, if you have a smaller table, always put them on the right side of the join, or like later when you are listing all of the tables that you join. That will help BigQuery use broadcast join, which means that every slot, one slot will read all of the rows from the right join, the smaller table, and this data will be shared, will be sent to every slot that are processing all of the transactions. It may seem like an overcome because every slot must have all of the products or product categories in this case, but it's much less for the shuffling. Yes, so this is a good one. And how you can minimize the number of rows that you are shuffling and you are joining? Let's say you want to give you have a query that you want to show what was the sales for each product. Yes, so you have let's say, but you want to show it per product SKU or product name. So the first approach is that you simply join products with transactions with products by product ID. And then you provide, like, OK, I want a SKU of the product and number of transactions for this SKU. And if I run this on BigQuery, let me try, maybe. OK, I can probably go even. OK, this is better. So with this very first naive approach, this takes around 14 slot time consumed. It's around 14 minutes of the slots. However, we could think about it a different way. So maybe it's better to first aggregate all of the transactions by the product ID. So I have it here in a subquery. So I have select product ID, sum of amount times price as a value of the transaction, and I group it by product ID. And having this table, then after this aggregation, I add the join with the product information to have the product SKU. This can be written also in other way if I use the common table expression, so I can somehow prepare the query here on top. So I see I have some kind of transaction aggregated data. So I first aggregate by product ID. Yes, select product ID, group by product ID. Like product ID plus the value of transactions. And these results of these aggregations, at the end, I join with the products. And if in the previous case we had 15 minutes of processing time, here it should be, it's always a surprise, it's only 6 minutes, right? So it's really worth it to aggregate early and to minimize the number of rows, minimize the amount of data that you are joining and shuffling between the different slots. Right, we can move on to the next tip. If you join, like this is mainly about how you should prepare or how you design your database, it's always better to join tables by integer. Integer is just an 8-byte data type, yes. If you have a string and by accident you have to, for example, join by SKU, which is a string, this will always take longer. It's not dramatically longer. It can be like 20–30% of the saving, but like if you can change it, it's worth it. We can move on. And the other thing on joining the columns, okay, we have this worst scenario that you have to join by strings, but please try to avoid using some functions during the join. Yes, so if you're not sure that if your data is clean and you suppose that maybe some products have SKU with some trailing or leading spaces, or there are things that are, you're not sure about the quality of your data, and you're running the join by trimming SKU on the left side, trimming SKU on the right side, BigQuery must provide, run these string operations on every record before it can join. Of course, it's much better to do all of this cleansing, to do this trimming in advance when you are importing data in your ETL or ELT processes. And if you want to take a look, what is the comparison? It's not that dramatical. Maybe we can move here. Yeah, so suppose that we want to join transactions with products. By the way, this is also always better way of building the joins, starting from the biggest tables to the smallest. I've been talking about it, yes. So this will be a hint for BigQuery, try to use the broadcast join, yes. So transactions is much bigger table than the products in this case. But here we're trying to suppose that we have a mess in the data, and sometimes the SKUs are with dashes or dots, or it must be cleaned during the join. It's not an optimal way. In this case, the query takes around, you can see it here, 4 seconds, but it consumed 32 minutes, so it was half of an hour. So it is already 2 or 3 cents, right? So you can transform it to money. But if you can skip all of these computations of the string functions and you just join by the string that is already ready, it is only 16 minutes. No, it's half of the cost. Right. Let's move on to the 5th tip. We're going to the where clause. So select, from, and where. Similarly, as in the case of joins, it matters expression of order of expressions in the where clause matters. So if you have a lot of different conditions in your where clause, always start with the ones that are the most selective. So for example, we have an example here that we want transactions only from this year, but also only for the one selected product ID. So it is much better to write it in this way, that first you want only transaction for one product. That should probably limit your amount of your data by 99% or something. And then only to these records you will apply additional filter saying, okay, I want only transactions from this year. And the difference may be quite significant, yes? So if we try the first way, it's 6 minutes of slot time consumed. And if we switch the order, and the call. It's 1 minute, right? So this the difference may be quite big. So, and of course, these examples are quite straightforward, and you can think it's okay, it's obvious. But it's maybe you can think about it like a general rule. So it's very often it's not only about 2 subconditions in the where, it can be 10 of them, or it's a maybe more complicated situation. So you can think about it. You always want to limit the number of the data as soon as possible. And the other hint for these expressions in the where clause is that one to prioritize the ones that are most selective, but also the ones that are easy to compute. So if you have some equality that is easy to compute, go with that first. But if you have some reg expressions or even or some more computation, this should be at the end, yes? Again, you don't want to run regex operations on all of your rows, just on the left ones that were left after previous filtering. Right. We can move on to the sixth hint. alter filter columns by their native types. This is quite obvious. I hope that nobody would try to put it on the left way, but suppose that you only want some transactions from like January 2025. You don't cast all of the data, 500 million transactions to string just to compare string. You operate on the data how they are stored in the BigQuery. This is particular, and of course, if we can run it here, that the difference should be very large. So if we are casting everything to string and take the just 7 left characters from the date, that took 2 minutes of the computation. But here, if you just do it properly and look for the data itself, it's just 2 seconds. And here, you may notice that I'm using slightly different table than in the past. This is transaction when I applied the partitions. Yes? So this is especially important when you have partition tables. So in a way, partitioning is when you apply partitioning to BigQuery tables, you tell BigQuery that we should store every partition in a separate files. I mean, here we have partitioning by this transaction date. So date from every transactions from every date are stored in a different files. And that allows us to very quickly prune or like get rid of all of the data that you are not interested in. Yes. So here the best part was that BigQuery was not opening 99% of the files, because we already knew that only some couple of files contained data from this January 2025. Yes. Right. Moving on. We are still about in the where clause, and anytime you want to compute some condition for the strings, it's always more performant to use like operator, like a Google like SQL-like, rather than regular expressions. Regular expressions are more powerful. You can express more intent there. But if you are able to accomplish your goals with like, it will be always a little bit faster. Yes. So you can think about it as a first step. And this is kind of specific to a specific use case. When you are using a not in clause, so when you are you're going to where, so give me all of the, I don't know, product reviews, where where user ID was not in some selected whatever, like you have some list that you don't want to include. It would be great if you can assure BigQuery that this list will not contain nulls. This will allow us to apply some faster algorithm. So whenever you are writing a query like this, maybe here I could show me all of the transactions where product ID is not in some kind of, I don't know, you have a strange list that you want to exclude from your query, and you're just taking select ID. And this query this query takes around almost 4 minutes of the computational power. But you know that in this table, ID is always not null. So you can say and ID is not null. And then seeing this query, BigQuery will know that it can expect that nulls will never appear on the list. So that allows us to run the query faster. It's around 3 minutes, right? I don't know what is the previous number, but it should be always faster. Right, moving to the tip number 9. Again, we are in these strange queries when you are applying where some ID in some set and other ID in other thing and so on. Generally, this is not the best way how you run your queries. It's always better to apply left joins. So you wanna see some you're left joining some additional tables, and then you can only say where some IDs are not null or are null, right? So prefer left joining tables rather than running subqueries. This should be always faster. Right, I think that we can move on here. Common table expressions. This is a very convenient way to write your queries to make them more readable, easier to understand, easier to write. And this works fine. Although you must remember that when running such a query, we are using these common table expressions as a macro. So before we run a query, we are trying to like somehow parse all of the CTEs and roll them to prepare one query that will be run. It's when you have a lot of CTEs one on top of the other, it's sometimes better just to change some of them to create temporary table. Yes. So then this part of the query will be just run first. We will temporarily store the results of this query, and then this can be used in any place below in your query, in your joins or subqueries or anything needed. Of course, with this approach, you can experiment. Sometimes this change will not change anything, but it's as easy as it is. Like if you just can replace with create temporary table, you can play and you can see if that helps to accelerate your queries. And then we're moving forward to the next closest of our SQL query, order by. Basically, if you are applying order by, always use this with a limit. Usually, like there are so little cases when you want to have all of your data from your whole large table ordered by something, and you need all of them. Like you will not read it manually, go through the list, right? So usually when you are applying order by, you want to like top 10, top 100, top 1,000 rows, and this helps a lot. Why this is so? If you take a look how the query is run by BigQuery, again, we have this distributed compute, and each slot is reading only part of the data. And if we are having this select star order by without any limitations, every node, every slot of BigQuery takes his part of the data, orders like sort it to make the proper order by, and then passes that to the final slot that must merge all of these lists. Merging many lists, like eventually all of these lists, all of these, let's say 500 million records will need to land in one final slot that must merge all of the sorted lists and provide the final order of the rows. That's a lot, and this even may be like there may be some out of memory errors or anything like exceeding the capabilities of a single node. However, if you apply the limit to the query, all of these nodes will already know that after all, we don't need more rows than these three. So even each of the row takes their part of the data. They are ordering, they are sorting the rows, and they see, okay, I found 5 rows, A, D, F, G, Q, but I know that not more than 3 will, after all, be needed. So I can already forget about the last 2. And to the final slot, only up to 3 rows are returned by this lower nodes. Yes? So this is a big change. And as I said, it's usually not the case that you really need to order all of your rows without any limiting. Okay, if you are trying to create a new table, create a copy of your table, like create table as, and you have some query like here, usually you don't need to do order by at all, because after all, BigQuery will not store your data in the order that you provided here. Yes? So you are creating the table, and we will find the most optimal way to store your data. We don't need to take your data in an ordered manner and then trying to save it to files. Yes? So forget about order by. Just give us the data, we will store them. But it's just because you ordered the data before saving it, it doesn't mean that we will somehow use it for storing. What is more, if you just want to copy the table as before, try not to create table as select star from the table, because that computes and that's costly. You can use the command copy, which will create. This is a free operation. This is at the beginning just the operation on the metadata. So we are trying to create some kind of shallow copy. And for the next updates, we are just tracking all of these differences between these tables. Yes. So very often you need just a temporary copy for a second because you need to play with it. Use the copy command instead of create table as select. And moving on, very often some functions you use functions, UDFs, and so on. First thing that may not always be applied, but you can use it sometimes. Whenever you need to count distinct values of the tables, you can use it with a regular approach, like select with count distinct, but you can also use the approximate count distinct function. And this is kind of good or bad, because it's much faster, but it's only approximate. So until you are fine having 1% error, this is the range of the error that we guarantee, it's much easier and faster to use these approximate functions. But of course, it's up to you. Like, if you will be asked for this 1%, it's probably better to have a precise numbers. We can take a look what is the difference here. But in the first approach, when you have just full count distinct, so like how many distinct products were sold every date. So it was around 10 minutes of slot time, but if you would approximate count distinct, it was 5 minutes. Yes. So again, sometimes you wanna have some ballpark numbers, just more or less. You can see that. And maybe just a general comment on all of these optimizations. It's when you write just ad hoc queries, they don't count that much. You can save probably a couple of cents or something like the small number, yes. But it's more important whenever you prepare some kind of dashboard or anything that will be used heavily by many different users. Of course, that makes much more sense. And especially when you're creating some software that will be generating these queries for the BigQuery, some dynamically generated queries, then you might think twice with techniques to apply, how to put all of these clauses in order so that it's cheaper and faster. Moving back to the functions that you can create and use in BigQuery, always try to use SQL UDFs. UDFs are user-defined functions when you can create some functions rather than JavaScript. SQL is native language for BigQuery. JavaScript always requires some kind of sandboxing, some security layers, and so on, because we need to be, let's say, more careful what JavaScript you are trying to run here. So, of course, you can't accomplish everything with SQL, but if you can, prefer SQL UDFs. And then I have I have just last three things, because I kept talking about what you can do to accelerate your queries. The good news is that we on our side are also working on optimizing BigQuery and how your queries could run faster. So there are three things that I could recommend. And in fact, I could just say that we recently launched. One thing is the history-based optimizations. So remember, I was saying that when you were joining the tables, you can provide the name of the tables or the order of the joins, like there could be different order of the joins. And especially when you have a lot of joins, like joining 10 different tables, it's not trivial to find out the best order, how to build the query plan so the query is run most efficiently. So that's why we implemented the history-based optimization. Whenever the same query is run over and over again, we are trying to apply different query plans and to track it what works best. And very often we see significant decrease of the times spent on computations. Yes, so we are trying to apply different strategies to the query plans and see what is working, and then once we find the best spot, we stick to the best way. When I'm saying that the same query is being run, of course we are trying to for us, if the query is the same shape by different constants, this is still the same query, yes? But generally speaking, if you have a query that is below some BI dashboard or in some ETL processes, over a time it should accelerate. Until a couple of weeks ago, this option required some manual enabling. But as far as I know, this is already enabled by default for all of the projects, so you should benefit from that. The other option that we introduced recently is something which we call optional job creation mode. So this is the way that the whole distributed architecture that I was talking about is maybe not necessarily for every query, especially for the small queries. Very often, for the small queries, it's much faster just to write them straight away rather than distributing the job to 200 machines, trying to track it and like synchronize all of them. So you can either do it here in the UI, you can say optional job creation, confirm, or you can do it with any API flag or any way you're running the query. But but generally speaking, it helps a lot for the short queries. The only side effect is that if you run a query with this mode, it doesn't contain a job, as we call it. So for the job, this is not, this didn't work here. Okay, but basically you will not have all of this metadata that were from the tracking, all of this distributed synchronization, but the query should run faster. This is also just a hint for BigQuery. So when you are saying this is optional job creation mode, we will try to run it on the one node just straight away. But if we see that this query actually is a quite big query and it requires all of this architecture, we will go with a regular approach. And the last thing that I had, it is an advanced runtime, we called it this way, and it was released very recently, and I think like 2 or 3 days ago it went generally available. So we really invested a lot, like I don't know, couple of, I don't want 1 or 2 years of quite a large team of engineers, how to bring enhanced vectorization and short query optimizations. So, and for some good queries, it really could accelerate them by 10 or even more times. Again, even last week, that required some enabling for the project. That's not the case anymore. The queries should have accelerated significantly in the past. So maybe to sum up, that was a kind of 15 tips how you could apply things to make your query faster. On the other hand, we are also working on the same area, how to make your queries faster and cheaper. As always with optimization, not every time every hint will work and accelerate your query. Sometimes it can be the way that you are applying things, but we already did that in our query engine. So it's always a matter of some craft and art. But I hope that you could use some of these hints in your work. Thanks a lot. That's all from me.